Hello, and welcome to the Go-Around Performance presentation. The subject of Go-Around Performance has been tackled quite a few times in the past years. We've discussed it in 2016 at the Engineering and Documentation seminars, at which we did a presentation and workshops to discuss it with the performance engineers. We've also discussed it with the pilot community in 2017. But since then, we've kept receiving more questions on Go-Around as it has a strong impact on your operations. So today, we'd like to address this subject one more time and to make it available for you online. I would like to start my presentation with a concrete example, which is the airport of Bogota. The Bogota elevation is 8,361 feet. And in terms of go-around, we are required to maintain a gradient of 3% up to 13,000 feet. In FlySmart, two fields enable to control go-around performance today. First, the go-around gradient field, and if you click on the runway, you can also access a go-around altitude field. For each airport, your performance engineering department can define default values for these fields, but the flight crew can update them. And the altitude field is not mandatory, it depends on the administrator settings. Now I would like to ask you a small question. What would you expect FlySmart to check in terms of go-around? A gradient of 2.5% with no reference to altitude? A gradient of 3% with no reference to altitude? A gradient of 3% at 11,000 feet? Or a gradient of 3% at 13,000 feet? So I'm not going to give you the answer immediately. We're going to discuss go-around performance a bit further, but you will see that the answer is not as simple as it may seem. As you know, go-around is a key point in aircraft certification. So I'm going to start this presentation by reminding you of the main criteria that must be considered for aircraft certification. You have to know that, originally, our performance software were designed to check the certification constraints. Then, we will take a look at the operational constraints that you operators face in your everyday work, because go-around performance is also key in operations and can be limiting. We will also take a look at the differences between certification constraints and operational constraints. And then finally, we will take a look at the performance software and at the possibilities that are available for you today in order to compute go-around performance. So the objective of this presentation is to make a clear status on the go-around performance today and of course to answer our little question about Bogota. Let's start with certification constraints. During certification, we have to comply with EASA CS25 and FAA FAR 25 requirements. In terms of aircraft performance certification, we need to demonstrate the aircraft capability of maintaining a minimum regulatory gradient during approach climb and landing climb. But we know on Airbus aircraft that the landing climb gradient is less limiting than the approach climb gradient. So we are going to focus on the approach climb gradient. In addition to this, the engine thrust time limitation that we know in takeoff is also applicable in case of go-around. So we have 5-minute toga thrust with all engines operating and 10-minute toga thrust with one engine inoperative. For approach climb gradient, the aircraft must be able to maintain a minimum regulatory gradient of 2.1% for two-engine aircraft and 2.7% for four-engine aircraft. This gradient is determined in the following conditions: one engine inoperative, toga thrust, gear up, and approach configuration. But the regulation only requests a point computation which can be done at airport elevation or above. In most cases, the minimum regulatory gradient for go-around is not limiting. Let's take an example of an A320 aircraft. For an A320 aircraft, the maximum certified landing weight is of 66 tons. At ISA temperature and up to 12,000 feet, the go-round limiting weight remains above the maximum certified landing weight. So the minimum regulatory gradient may start to be limiting at high altitudes and high temperatures. The second question that we have to answer during aircraft certification is the fuel jettison system required or optional? To check this, the certification criteria imposes that the aircraft is capable of maintaining a minimum regulatory gradient of 2.1% or 2.7% for four-engine aircraft in case of return to land up to the maximum takeoff weight minus 15 minutes of flight. If we go back to our example of A320 aircraft, when this aircraft is not performance limited, the maximum takeoff weight is of 78 tons. Minus 15 minutes of flight, this takes us down to 76 tons. At high altitudes, this is higher than the weight limited by go-round. In order to avoid this situation, specific procedures were developed. First of all, we have taken benefit from the acceleration which is authorized by the regulation. Indeed, the regulation authorizes the use of a go-round speed that goes up to 1.4 of VS1G. Using a higher speed will help us achieve a better climb gradient. In addition to this, for overweight landing, we have developed a specific procedure that enables us to use configuration 1 plus F for go-round when landing in configuration 3. The use of a lower configuration will also permit us to achieve a better climb gradient. With this procedure, using a lower configuration and acceleration up to 1.4 of VS1G, return to land is no longer limiting. The acceleration and the use of configuration 1 plus F are used here in case of return to land. But these two options may also be used for non-overweight situations. The acceleration is available on most aircraft types, and the use of configuration 1 plus F for go-round is a specific option available for high-altitude operations on some aircraft like the A319 for instance. As a result, the fuel jettison system is not mandatory on Airbus aircraft. It's proposed as an option on the A330, A340, A350, and A380 aircraft. So now let's go back to FlySmart. In line with the certification requirement, when we do a landing performance computation, FlySmart will perform a point computation, which is done at a given altitude, which can be customized by the user. And the same check is done for the dispatch and the in-flight computations. However, for daily operations, airlines have to face different constraints. In operations, some airports published missed approach gradients like the one that we saw in the beginning of our presentation for Bogota. The missed approach gradients are determined following PANSOPS rules. They assume normal operations, meaning all engines operating. PANSOPS set the international standard. However, depending on the country, local regulations, like TERPS in the US, may provide different rules. In this presentation, we will only focus on ICAO standards. According to the ICAO PANSOPS, a published missed approach procedure shall specify a point where the procedure starts, the decision altitude or height, a gradient, and a point where the procedure ends, the missed approach altitude. So to design the missed approach procedure, airport authorities determine a plan in order to meet ATC constraints, non-overfly for some areas, traffic management constraints, for instance, or of course in order to clear obstacles. So the aircraft shall not break through this plan. The missed approach gradient is published only when it's higher than 2.5%. So if this gradient is not published, 2.5% applies. The regulation that applies in terms of operations is no longer CS25 or FAR 25. The operational constraints are given in the AirOps for EASA and in the FAR 120-91 for FAA. And this is a summary of the Airbus interpretation of these regulations. The minimum gradient of 2.5% or the published value, if higher, must be maintained with one engine inoperative. So even if the procedure design is done based on all engines operating, the operational regulations require to consider one engine inoperative performance. But what if the published gradient is limiting? EASA in guidance material and FAA in advisory circular give the possibility to the operator to define an alternative means of compliance. This alternate procedure shall ensure a safe missed approach, avoiding all obstacles, and shall be approved by a competent authority. We will come back to this alternative procedure later in this presentation. Now that we have spotted the difference between our software, designed for certification constraints, and the operational constraints, let's take a look at the go-around computation that you can do today using the performance software. First, let's take the example of Toulouse, ILS approach on runway 14 left. No gradient is published for this approach, so the minimum regulatory gradient of 2.5% applies. This minimum gradient must be maintained up to 4,000 feet. The published procedure defines a plan below which it is forbidden to fly. For our example in Toulouse, we have a 2.5% plan that must be maintained up to 4,000 feet. The performance software only performs a point computation. The aircraft climb capability depends on the altitude at which we do the computation. So depending on whether we compute the go-round gradient at the decision altitude, the airport elevation, or the missed approach altitude, the maximum weight limited by go-around will not be the same. Here are the maximum weights limited by go-around for our example in Toulouse. The threshold and decision altitude results give better values, but are not on the safe side. The go-around weight computed at the missed approach altitude is the lowest, but is also the most conservative. In this example, up to the missed approach altitude, the maximum weight limited by go-around remains above the maximum landing weight. So we are not limited by go-around on this airport, which means that go-around can be computed at the missed approach altitude. So for the flight crew in FlySmart, for Toulouse ILS approach on runway 14 left, we can thus expect a gradient of 2.5% to be checked at 4,000 feet. Nothing surprising at this point. Now let's go back to our example of Bogota ILS approach on runway 13 left. According to the published missed approach procedure, we have to maintain a gradient of 3% up to 13,000 feet. So the published procedure defines a 3% plan that must be maintained up to 13,000 feet. For this example, if we compute the go-around gradient at the decision altitude, at the threshold, or at the missed approach altitude, we get the following go-around limiting weights. The threshold and decision altitude computations are not limiting, but we're not on the safe side. And the missed approach altitude is very limiting. The objective here is not to have a 3% gradient at each point along the flight path. The objective is to have an average gradient of 3%. With an average gradient of 3%, the gradient at start of climb will be higher than 3%. The gradient at the missed approach altitude will be lower than 3%. As the software only performs a point computation, we need to find the exact altitude for which a 3% point gradient would correspond to an average gradient of 3% from start of climb up to the missed approach altitude. For specific airports like Bogota, it's the job of the performance engineer to determine and communicate this information and this altitude to the flight crew. In Bogota, in order to simulate an average gradient of 3%, we must consider a 3% point gradient at 11,000 feet. And this value shall be communicated to the crew. As a result, for Bogota ILS approach on runway 13 left in FlySmart, we can expect a gradient of 3% to be checked at 11,000 feet. And your performance engineering department can define 3% and 11,000 feet as default values for Bogota Airport 13 left. But what if the published gradient is still limiting even when using the average gradient method? As mentioned previously, the regulation gives the possibility to define an alternative means of compliance. The way to define this alternative procedure is not detailed in EASA or FAA regulations. But some local regulations, including the FAA, recommend checking obstacle clearance following takeoff criteria with a net flight path. As obstacles cannot be inserted directly into FlySmart for go-around, it is the job of the performance engineer today to determine the go-around gradient at altitude to be inserted into FlySmart and to communicate them to the flight crew. To conclude, the objective of this presentation was to remind you the differences between the certification and the operational world of go-around performance, and to highlight the fact that our performance software was mainly designed to check the certification constraints. Today, the good check of go-around performance requires performance engineering offices and airlines to determine the go-around data to be used in FlySmart and to communicate this information to the flight crew. As I told you in the beginning of this presentation, we have organized several workshops to improve the go-around performance in our software. So a new go-around function is currently being developed in FlySmart, which will permit you to check the average go-around gradient, but it will also give you the possibility to check obstacle clearance for go-around in airports with very limiting go-around gradients. This new functionality will be available in FlySmart for both Windows and iPad by the end of 2019. Thank you.